Hey everyone, so I want to talk about the penultimate topic in this unit, which is all about inclined planes. Again, this is another one of those very specific cases where we're going to have to use F net equals ma, Newton's three laws, friction, but we're going to have to alter it a little bit and change up how we approach the problem because of the weird setup. So, as the name implies, inclined planes are essentially objects that are placed on ramps, surfaces that are raised up at one end. Because of the way that it's set up, we have to kind of approach it a little bit differently than what we've done before. So, for example, let's start with just a regular FBD. Now, if we have an object on a ramp, we know that there's at least two forces acting on it right now. There's gravity pulling it down, and the normal force going up at some angle. Now we know that the normal force has to go up at an angle like this because the normal force, by definition, is perpendicular to the surface. So gravity goes straight down towards the center of Earth, and the normal force goes up at a right angle. Now, normally, when we have an FBD like this, we can see that Fn is at some angle. We don't like that. We would break up the Fn into an x component and a y component. And then we would, be able to add the y component of Fn with Fg to get a net force and all that stuff. But the issue here is that if we do that, we end up getting the unbalanced force caused by the angle of Fn going directly to the right. But we know for a fact that the object doesn't do that. It doesn't go in that direction. The object, if we place it on a ramp, we know it's actually going to go down on an angle, going down the ramp, parallel to the ramp. So breaking up the Fn into an x and y components doesn't make sense because of the fact that the object won't be moving in the x and y direction. It's going to be moving in a slightly tilted angle. So so instead of breaking up the Fn into x and y, what we're going to do is take the Fg and break it into components so that one of the components is going to be perpendicular to the incline and the other one's parallel to the incline. Essentially what we're doing is we're rotating our reference frames. So this is the two forces that Fg is going to be broken into. This perpendicular version or component, we're going to call it aptly the perpendicular component, and the parallel component is called the parallel component, the parallel force. So instead of breaking Fn into components, we're breaking Fg into components. And like I said, it's being done so that everything is now with respect to the incline. We now have forces that are perpendicular and parallel because that's the direction that the object's going to move. It's going to either move perpendicular or parallel to the incline. And again, like I said, we're essentially rotating the reference frame. If I rotate the inclined plane so that it's now flat, we see that the normal force acts like it should be, going straight up. Now Fg is the one that's at an angle. So now it makes sense that we break up the perpendicular into a vertical, into the new vertical, and this parallel part for the new horizontal. Now, the real question is, how are we going to calculate F parallel and F perpendicular? Well, first and foremost, we know that these are components. So that's going to give us a really good hint as to how we're supposed to approach this. We know from previous topics that when we are looking for the components of something, we basically multiply it by either sine or cosine, depending on whether we're looking for an x or y component. We're going to do the same thing here. Because these are the components of the weight, that means we're going to take the Fg and we're either going to multiply it by sine or we're going to multiply it by cosine. So which one is it? We'll derive it first, but then once we derive it, you won't have to do it again. So let's just say that the angle of the ramp is some angle of 30 degrees. Now, Fg goes straight down. If I look at the shape caused by Fg going straight down and this little section of the incline, I can see that I have a right triangle. As we know, the right triangle has the other two sides equal to 90. So that means that this angle up here must be 60 degrees, since 30 plus 60 equals 90. Now, if I look at this shape, this is also a right triangle. So this is going to help me out. But I also know that by definition, this green line is a perpendicular line. It's perpendicular to the surface. So this angle right here is 90. This angle is 60. That must mean that this angle has to add up to 90, which is going to be 30. Since, again, it's perpendicular, these two should add up to 90. 30 plus 60 is 90. So we see that the main takeaway is that the angle that is within here, in this little right triangle, formed by the hypotenuse of FG, the component F parallel, and the component F perpendicular, is the same angle as the ramp's incline. Now that I have that, what I can do is we can use SOHCAHTOA to figure out what F parallel and F perpendicular are. F parallel, well, that's opposite the angle, and FG is our hypotenuse, so we're going to use sine, plug my numbers in, and we get that F parallel is equal to FG sine theta. Do the same thing for the perpendicular component. It's adjacent, so we're going to use cosine. So cosine is the perpendicular over FG, so we end up getting that the perpendicular component is FG cosine theta. So in the end, what we end up getting is that the parallel component is FG sine, and the perpendicular is FG cosine. All right, cool. All great and dandy. Now the problem is we need a way to memorize this. So these equations aren't on the reference table. Like I said, because they're components, you're kind of expected to be able to know how to derive them. So one way that you can remember is just using a little rhyme. Unfortunately, the parallel is the only one that has a nice rhyme. If you think about it, the parallel force causes this object to go down the ramp, or if this is a box, would slide down the ramp. So what we would say is that this force, which causes the blocks to slide, is the force that causes that we end up signing. The force that slides is the force that signs. So you might hear me say this in class where I say sine and slide and sine, in order to remind you, what force is going to be equal to sine theta, or FG sine theta. Unfortunately, the perpendicular doesn't have as good of a rhyme. You don't need it since sine and slide work so well. You just remember that the other one's cosine. But this one, it's the force that crushes is the force that cusses. I know that I mispronounced cosine there, but it's the only way I can make the rhyme fit. Essentially, this perpendicular component is actually what's pulling it into the ramp and providing the normal force coming from it. So it's crushing, pulling into the ramp, therefore it's cosine. All right. Now, normally when we have an object on like a flat table, the normal force in the absence of any other forces acting vertically would be equal to the weight pulling down, because the normal force acts essentially as a balancing force in this case, in a lot of the cases that we've been doing. The same thing happens here. The normal force is going to be balanced by whatever is opposite it. In this case, that's the perpendicular force. So try to avoid going to the default Fn equals Fg, because that's not actually ever the case. But it's especially not the case here. Fn is going to be equal to F perpendicular. Again, if you get into the habit of drawing the FPD, you won't have this issue. I should make a very quick note right now that this FBD, where you include F perpendicular and F parallel and omit FG, is only when you're drawing the FBD for yourself. Remember, when you draw an FBD for me on a test or for the AP, you are not expected, or you're not, they do not want you to include components. And F parallel and F perpendicular are components. So instead of this, you would have drawn the first FBD that I showed you, where you had Fn and Fg. That is the FBD for me. This FBD is the one for yourself. And if we decide that we want to find acceleration, then in this scenario at least, the net force that's creating the acceleration is being caused by F parallel. Now, there might be other forces like friction or an applied force or something else that could be acting on the box, and in that case, that would be incorporated into the F net. But essentially, what I'm trying to get at is that the parallel force is a contributor to the net force that causes the acceleration. Fn and F perpendicular do not take any part in the net force. All right, so let's do a few practice questions. So pause the video, work itself, and we'll go in a second. All right, so this first one, they want to know the forces acting on this object. Now notice it might be hard to see some of these symbols. They have Fn for the normal, Fw for the weight, and Ff for the friction. We know that the normal is going to go up and to the left because it's got to be perpendicular to the surface. The only one that does that is D. And just to double check, all the other forces make sense. Fw, the weight of the object, goes straight down, and friction always acts parallel to the surface and also acts perpendicular to the normal force. That's one thing that you want to make sure that you have, that normal and friction are always perpendicular. All right, here's the next question. Pause the video, work itself, and we'll go over in a second. All right. So they want us to figure out what is the net force causing the acceleration. So they give us this diagram. So the first thing I actually want to do is just draw in the FBDs, the other forces. Again, this is the FBD for myself. So or for the worker, it's not an official FBD. So I'm going to have Fn, F perpendicular, and F parallel. And we can see right off the bat that F parallel is what's causing the acceleration. It's the only one in the parallel direction that's pointed in the direction of acceleration. So F net is the parallel force, which is going to be Fg sine theta. Plug in my 8 newtons and sine 15, and we end up getting 2.07 newtons. All right, so let's go to this one. So pause the video, work itself, and we'll go over in a second. All right. It's a very basic question. We have a smooth surface, blah, blah, blah. First two parts are pretty straightforward. Calculate the perpendicular and parallel components. So again, we start off with our equations for the perpendicular, Fg cosine theta. Plug our numbers in. Make sure that we take this 30 and multiply it by 10 to get the 300 newtons. You probably, just to be on the safe side, you should probably write out the work. I actually do have enough room, but I was just doing this very quickly. You get 300 newtons times cosine 30 degrees, which gets you 260 newtons. The parallel component, we do pretty much the same thing. Fg sine theta, flip that cosine to a sine, plug and chug, and we get 150 newtons. All right, for part C, we want to do a quick little FBD again. So here's what our forces look like. If we look at this, the normal force is opposite the perpendicular. So what we're going to do is do some of the forces in the perpendicular direction. Fn minus F perpendicular equals 0. So they have to be equal. Therefore, Fn is 260. And then to calculate the acceleration, again, the only force that's unbalanced, that's acting in the plane of acceleration, is going to be that F parallel. So the net force is the parallel force. So I'm going to take that 150 newtons that we got before, divide it by 30, and we end up getting 5 meters per second squared. All right. 39 is essentially the exact same question. So we'll go over this really quickly. Pause the video, we'll go over a second. All right. So going over to part A and B, again, plug and chug into the equations. We end up getting the perpendicular component is 50 newtons, and the parallel component is 86.6 newtons. All right. So for this next part, what we're going to do is same thing where we draw our FBDs. Fn is equal to the perpendicular component, so it's equal to 50. Again, the net force is the parallel component, plug and chug, and we get 8.7 meters per second squared. Easy enough. All right, so we'll move on to 40. Pause the video, work itself, and we'll go over in a second. All right, once again, I want to start off with drawing my FBDs. Now from here, we're trying to find F. Now, because of the fact that it says that the block is pulled up at a constant velocity, I know that all the forces have to equal, the sum of the forces have to equal zero. So Fn and F perpendicular equal to zero, and F and the parallel and the friction force equal to zero. So because F acts parallel, what I'm going to do is sum all the forces in the parallel direction. So we get F going up minus the friction going down minus the F parallel force going down, all equals zero. So what I'm going to do is just set the force going up the ramp equal to the two forces going down. So it's going to be equal to FF plus FG sine theta. Plug our numbers in, and we end up getting 8 newtons. Be careful with the numbers that they give you. They kind of flip-flop between giving kilograms and newtons. You know, just don't get caught accidentally getting in the habit of multiplying that number by 10. All right? And this is going to be the last problem that we do today. So pause the video, work itself, and we'll go over in a second. All right. So with this one, they want to know the minimum coefficient of friction needed to keep them at rest, as Santa Claus is on this roof. So I know that the equation that I want to use is going to be FF equals mu Fn. So I'm going to need to figure out the friction and the normal force. Now I'm not drawing the FBD in here just because it takes a while to do it on PowerPoint, but I know that the friction that's going up the ramp is going to be balanced by the parallel force going down the ramp since it is at rest. And I know the normal force pulling, going away from the ramp is going to be balanced by the perpendicular force going into the ramp. So from here, I get that the friction force is equal to Fg sine theta and the normal force is equal to Fg cosine theta. Now, one thing I want to note is that you'll notice that I'm not going to plug the numbers in right away. And that's because there's a very unique solution to this. So I'm going to actually leave it in these variable terms, Fg sine theta and Fg cosine theta. Now we can go back to the friction equation, FF equals mu Fn. I take the Fg sine theta, plug it in for FF, take the Fg cosine theta, plug it in for Fn, and hey, look at that. We have an Fg on both sides. That means I can divide them out and the Fg's cancel. Also, I have a sine theta and a cosine theta. I can divide the cosine over and I'll end up getting sine theta divided by cosine theta, which, if we know our trig functions, is tan theta. So the really interesting thing is that mu, the coefficient of friction needed to keep this at rest, actually is going to be equal to tan theta. And it has nothing to do with the weight. It is all about the angle. In fact, I should probably note that, as we know, this is technically less than or equal to. So what this is actually saying is that the coefficient of friction is actually going to be greater than or equal to tan theta. So it at least gives us a minimum value to what mu can be, that it's based off of the geometry, if you will, of the surface rather than what is on that surface. So regardless of how heavy Santa Claus is or how light Santa Claus is, as long as the material between the two doesn't change and that angle doesn't change, it will remain at rest. So we plug in the 45 degrees and we actually get that the coefficient of friction is at least 1. It could actually be greater than 1, but it has to be at least 1. All right. And that's about it. Now, the questions that we've done so far are pretty much the Regents level type questions. We'll do a few more AP style questions in the next video. The next video is going to be fairly short. But I just want to point that out, that a lot of these, with the exception of 41, were Regents level. 41 was actually, it had parts taken out to make it a little bit tougher. But for the most part, there's really not too much that we can do. And you'll notice in the next part when we kind of bump it up to AP level, It's still not that difficult. It's just a little bit longer. So if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.